All right, so here we've got our picture of our hydrogen atom based off of this formula, telling us how large it gets as the states change. As you go from, say, a low state, like n equals 1, the ground state, up to n equals 4, it's going to get very large. Okay? And then you have n equals 2, n equals 3 orbits between them. So these orbits keep on going. There's not a limit to the value of n. Remember, n can go from, starts at 1 and counts all the way up with no upper limit. Okay. And on this side, I've got a picture kind of like the one I had last time, but more a little broad. You'll see why I drew it this way, but basically it's the same thing. It's like a bunch of steps, but each one is associated with an energy. So here's E1, the lowest energy, negative 13.6 eV. Here's E2, negative 3.40 eV, and all the way on up. And I didn't really label them past E5, n equals 5, because they got so close together. As n gets larger and larger, they get so close together that they're almost a continuum, way up here towards 0. So they're kind of blurred together up there. But down here, they're discrete. I mean, they're all discrete, but you can really see the separation. These are just energy levels, like stair steps. Okay. Now, normally, a hydrogen atom, if you go out, to Atoms R Us and purchase a box of hydrogen atoms, they will be in the ground state. That's where they live, because the electron is attracted to the proton, right? So they want to be as close together as possible. N equals 1, right? Down here, their distance is only a naught, 1 a naught. So they're as close as they can possibly be. That's where they like to be. That's where atoms go when you leave them alone. Almost always, not always, but for our money, yes, they return to their ground state. Okay, to their lowest energy state. Just like when you throw a ball in a hole, it goes to the bottom of the hole. It doesn't park somewhere, halfway down the hole, on the edges of the hole. It goes to the bottom. Okay, so in the same way, the electron will get as close as possible to the proton. The ground state's where it likes to be. But let's say that we give it some energy, we kick it up to a higher state, and we're going to talk about what happens when you do that. When you somehow get an electron from the ground state up to a higher state, it's going to return to the ground state, like the ball returning to the bottom of the hole. Okay? That's what will happen. It will seek its lowest energy state. But it doesn't have to go directly. Suppose we kick it, and don't worry about how this happens. Light can do it. Photons can do it. We kick an electron from the n equals 1 state up to the n equals 4 state. It's going to go back to 1. It wants to be there. Like throwing your pin up. It wants to be back on the floor, right? It wants to be on the floor. That's the lowest energy state it can find. You might somehow lift it to a higher energy state, but when you release it, it'll go back. I keep doing this. So we can bring the electron up to the n equals 4 state, but when we let it go, it's going to return to the ground state. But it doesn't have to go directly to it. It can jump from 4 to 3 to 2 to 1. It can go from 4 to 1. It can go from 4 to 2 to 1, go from 4 to 3 to 1, or it can go directly from 4 to 1. So let's think about transitions like that end at the ground state. Not all of them. There's an infinite number of them, right? Because infinite number of excited states. All the states that are not ground state are known as excited states. So these up here are excited states. And this, of course, is the ground state. So when you put it in an excited state, it returns to the ground state. Let's look at transitions that go from excited states down to 1. I'm not going to draw all of them. Like I said, that would be an infinite number. But let me draw a few of them anyway. Okay. Let me think of a color that's going to contrast with the orange here. We could have, if we could have remember, we're dealing with transitions that end at the ground state. So we have one that goes from here to there. Okay. That's like going from They're there. Right, n equals 2 to n equals 1. The energy drops, it goes from negative 3.4 eV to negative 13.6 eV, and it goes from 4 a naught radius down to 1 a naught. Okay, so those two transitions are the same. We also can have one that goes from 3 to 1, right? Right. We also have one that goes from 4 to 1, 5 to 1. All these transitions are possible. They're not necessary. If we put it in the n equals 5 state, it can go from 5 to 4 to 2 to 1, or from 5 to 3 to 1. But these are possible transitions that end at the ground state. I'm going to go all the way up to E6. Okay, so the third line from n equals 4 to n equals 1 is this transition right there. So the first three arrows here, 2 to 1 is right here, 2 to 1. 3 to 1 is right here, 3 to 1. 4 to 1 is right there, and I don't have any more in this picture because I don't go out beyond 4. I go up to 6 in this one. Okay. Okay. We could also have transitions that end in 2. We could have them go from 3 to 2, 4 to 2, 5 to 2, 6 to 2, like that. We also have transitions, so that would be 3 to 2. So our 3 to 2 would be this one right here. Our 4 to 2 would be right there. We also have transitions that end at 3, right? From 4 to 3, 5 to 3, 6 to 3, etc. And we can go on up. Okay. We can go on up. And we can also draw here our n equals 4 to 3 transition right there. Now, there are far more transitions in this picture than this picture because I included the 5 and 6 levels here. I did not include the 5 and 6 levels here. Okay? But here's the clip and save point to all of this. With every transition downwards, whether you're going from 3 to 2 or from 2 to 1 or from 7 to 5 or from 5 to 3 or from 20 to 1, every time that happens, the atom emits light. So when this happens here, you go from 3 to 2. When that happens, let me see what's good color here. When this happens, when this transition happens, boom, the atom emits light. When an atom goes from 4 to 2, the atom emits light. Each one of these transitions produces light. Okay. This formula, the transitions formula, the third product of the Bohr theory, tells us what wavelength we get when we go from NF to NI. I mean from NI to NF. Okay? It tells us what wavelength we get when we go from NI to NF. So all these transitions produce light, but every transition produces a slightly different color of light. And the 4 colors that we see in the hydrogen spectrum. Remember the 4 colors? The red. There was also a blue. And then there were 2 deep purples. Like that. Remember the spectrum with the 4 wavelengths? Those 4 lines come, it turns out, from these 4 transitions right there. the 3 to 2, the 4 to 2, the 5 to 2, and the 6 to 2. Those are the only transitions out of this infinite number of them that show up in the visible part of the spectrum. Those 4. Okay? So that's what's happening when we look at hydrogen. When we put hydrogen in a tube and we put it in an electric field that points down and up, then down and up, it ionizes the gas. But those free electrons combine back with protons, and as they do, they cascade down these energy stairs back to the ground state. And as they cascade down the energy stairs, every step they take, every time they fall from one state to another, they emit a different color of light. All of these steps, the ones that end down on n equals 1, these transitions are all ultraviolet. All of these up here are infrared. But these in the middle, the ones that end at 2, are visible. That's the Bohr theory. That's the deal.